Hey everyone. For today's calculus class, we're going to actually take a look at, it's kind of a hack of the integral by parts method. So what you're learning here, a lot of students will just call this a tabular method, but it really is just integral by parts, and calling it a hack, I don't know. Maybe it is, but it definitely speeds things up, which I'm sure you're going to be interested in. But the drawback here is that it is a lot easier to make mistakes with the integration. We'll talk about that more as we take a look at the method over here. So, like I mentioned before, this is a hack of the integral by parts. In particular, uh, it's going to be a table, a tabular method. So when we do this method, remember that you are never required to do the tabular method. That's kind of important for you probably. It's not a requirement for you to learn how to do this. However, it is faster. So let's see what it is. So part one, you're going to choose, no, well, we're going to choose, Part one, we're going to choose ourselves u and dv according to Lyautey, and we're going to write them in the first row. So let's pretend I didn't have the first row here, and I'm looking at this. I identify my factors. Got 3x squared, and my second factor is e to the x. And I take a look at those two, and I say, 3x squared is algebraic, e to the x is exponential. That means that 3x squared is going to be my choice for u, which is what we got over here. And e to the x is going to be my choice for dv. Notice how the dx isn't really going to play a part in this. So that's one reason why maybe students would choose to use this method. And here is the point. We're going to go ahead and take derivatives of u. So the derivative of 3x squared is 6x. The derivative of 6x is 6, and the derivative of the derivative of 6 is 0. On this side over here, the derivative or the antiderivative of e to the x is e to the x, the antiderivative of e to the x is e to the x, etc. Which brings me to why this method, or the drawback of this method. And the drawback here is that, well, you're going to have to do these antiderivatives really quickly and kind of in your head. So if you don't have a fluency with taking antiderivatives, then this method is almost useless to you. The other drawback here is that it's really easy to forget that the right side here is antiderivatives. So I'll see some people take the derivative of the u column and then take the derivative of the dv column. Now the question is, when do you stop adding rows to this table? Because we could have kept on going here. And there are two conditions for stopping. Number one, you want to stop when the u column gets to a 0. That's kind of preferable. Or if the column doesn't get to 0, you're going to stop if the product is integrable. So what we're going to do is we're going to take multiply the product here across here. So 3x squared times e to the x is 3x squared e to the x. 6x multiplied by e to the x, that is 6x e to the x, etc., etc. Notice that when we get to the bottom, the product is going to be 0. Okay, which means that we're stopping. Okay, we probably could have stopped over here at 6x e to the x because that is an integratable product, but since we knew that we were going to get to 0, we went to 0 because it is preferable to get to 0. This is the 0 I'm talking about right over here. It's preferable if you get to that 0. Okay, once you get to that 0, okay, I'm gonna have to scroll in between. Actually, I don't have to scroll in between. I have a computer. We're going to multiply diagonally, starting with 3x squared and e to the x. So 3x squared multiplied by 3 to the x, that's this right over here. Okay? And then since it's my first arrow, the first multiplication is always positive. My second multiplication is 6x multiplied by 3x. Remember, it's a down diagonal, and that gives me this factor right, or this product right here. Because it's my second product, it's going to be negative, and we're going to alternate positive and negative. Okay. My next diagonal is going to be 6 multiplied by e to the x. So 6 multiplied by e to the x. It's my third product, so it's going to be positive. Remember, we're alternating positive, negative, positive. And then since I'm at a 0 now, I can multiply that last one through, which is 0 multiplied by the same, and I get a 0. Okay. So that's how I know to stop. The antiderivative of 0, of course, is 0. Moving back down over here, that's the antiderivative, really. 3x squared e to the x minus 6x e to the x plus 6x e to the x plus that constant from this antiderivative of 0. Like always, you can do some factoring here. It looks like you want to factor out a 3 and an e to the x, and that gets you to the result. Pretty easy, right? I think it's pretty easy. It makes things a lot quicker, and we will see that in this next few examples. But we should talk about some wisdom here. And firstly, this method works really well if your choice of u is a polynomial. If you have u as a polynomial, you can bet that you're going to get down to a 0, which makes this really nice. Lastly, remember to, not lastly, what am I saying? Next, remember that you're going to integrate that dv column. A common mistake is doing finding the derivatives of both columns. And it is preferable to get to a 0. However, and this is the one that they don't really teach you often, you can stop this process at any time as soon as you see that the product is integratable. Okay. Since the only entry in the product column is a final entry, you may want to do so mentally. So don't remember what that was when I wrote that. I think I do, but let's just move on from here. So we're going to fill out this together. Okay. Let's see. What do I have here? I've got a natural log of x, and that's the only factor I have. So that dx is going to naturally be my choice for dv. So that, since there's nothing here, we're going to use 1 for dv, and we're going to use natural log of x for u. Let's take the derivative of natural log of x. It is 1 over x. Let's take the antiderivative of 1, and that is x. And we're going to multiply across 1 over x times x. That's equal to 1. So we've got an integratable product now, and we're going to stop the process. If you went another step here, you wouldn't necessarily get something that is integratable. But since this is integratable, we're just going to stop. Okay. Natural log of x times x minus the integral of the last row. So minus the integral of 1 over x multiplied by x and then dx. multiplied by that last row multiplied together. Do a little bit of algebra. Now take care of that last integral. The antiderivative of dx is just x. There you have it. That's the antiderivative of the natural log of x. Maybe it'd be a good idea if we looked at another example here. So let's try another example. Okay, antiderivative of x squared plus 1 multiplied by sine x. And let's get our uv column going on here. uv and udv. And let's figure out which one's which. We've got this first factor, x squared plus 1. This second factor, sine x. It looks like x squared plus 1 is algebraic, or it's a polynomial. So we'll allow that to be u, x squared plus 1, which means my dv is sine x dx, but I'm not going to bother with the dx part in my column. So take derivative of u, that's 2x. Derivative, or antiderivative of sine is negative cosine x. I said because you really got to think. It's tempting to take the derivative here. Okay, is 2x cosine x, is that integratable? No, it's not integratable. So let's go ahead and take another derivative. The derivative here is 2. The antiderivative of negative cosine x is negative sine x. And is 2 times negative sine x integratable? Now that answer is yes. So we could stop the process here. Okay, so we could stop here and construct this together, and you would get x squared plus 1 multiplied by multiplied by negative cosine x, okay, minus 2x multiplied by negative sine x. And then the next one is plus the integral of 2 negative sine x dx. So that's if you stopped over here. Okay. Or if you saw that the next line was going to be a 0, we could get to 0, and this brings me to cosine x. And that brings me to number 2, which is x plus 1 positive x squared plus 1 multiplied by negative cosine x minus 2x multiplied by negative sine x plus 2 times cosine x. And then typically when we see the 0 here, we stop and put a plus c. So look at these two. If you took this antiderivative of 2 times negative sine x, you would get 2 cosine x. So you can see why it's kind of preferable to get to that 0, because once you get to the 0, there's no more integrals. So this is actually the answer. I'm going to clean this up because that's what we do. And this is plus 2x sine x. And then this is plus 2 cosine x, and then plus constant. So it's kind of up to you where you want to stop. Again, conventional wisdom is keep going, and if you see that you're going to get to a 0 eventually. Otherwise, if you're not going to get to a 0, like what we have here, stop as soon as the product becomes integratable. Here's another example, and this is it says a curious case. So let's see, how curious is this case? Let's take the derivative of cosine, and we get sine x. Oh, I'm sorry, we should have found the product. That's e to the x cosine x, okay? Actually, I should have stopped and gone back over. This two factors here are cosine x and e to the x, and we have a trig factor and an exponential factor. Trig is a little higher up on the list than exponential, so we'll set cosine x be our u and exponential e to the x be our dv. That brings us now to this row. All right, so we have u, derivative of cosine is sine, antiderivative of e to the x is e to the x. Okay, that gives me e to the x sine x as my product. That's not integratable. Let's take another derivative. The derivative of, did I mess up? Yeah, I did. That should be negative sine. The derivative of negative sine is negative cosine x, and the antiderivative of e to the x is e to the x, and that gives me negative cosine x e to the x. And you're saying, well, why did you stop here? What's so funny about where this is in the chart? And what's so funny is that the product is the same thing as the integrand that we started off with, give or take a constant. So our integrand here is cosine x e to the x. Our product here is cosine x e to the x multiplied by negative 1. So it's kind of the same thing. And this is like a circular integral. So we're going to stop here and we're going to put things together. So the first thing we're going to get put together is cosine x times e to the x. Cosine x times e to the x. Minus negative sine x multiplied by e to the x. Negative sine x multiplied by e to the x. And then now we're at our last row. So we're going to add the integral of negative cosine x and e to the x. Negative cosine x and e to the x. So add the integral of the last row. Okay, once you've done that, you're going to do some algebra. So you're going to add the integral of cosine x e to the x to both sides. Notice that the effect of that is on the right side here, these two cancel out. That's a pretty bad choice for a highlighter color. So we're going to cancel out with algebra, adding and subtracting this integral on the right side. And on the left side, since I have cosine x e to the x plus another integral of cosine x e to the x, that gives me 2 cosine x e to the x, and that's equal to this sum right here. Of course, we did some integration, so there is a plus c that's there. So we're going to put the plus c here, do a little bit of factoring, or I guess we didn't factor here, but we're going to divide that 2. So we're going to take this side and we're going to multiply by 1/2. We're going to take this side and we'll multiply by 1/2 also. And that brings us to our antiderivative, which is 1/2 of cosine x e to the x plus sine x e to the x plus constant. Okay. This is a little bit about that integration, but like I said before, we've been integrating all along. So that constant is always there. We just kind of choose to write it there at the very end. So that is our tabular method. If we wanted, we could take a look at a different method or a different way of doing it, but it's really kind of the same thing. So that brings us to what were the important ideas here. So firstly, that tabular method can speed up the process of integration by parts. if you have a really good fluency with antiderivatives. Secondly, the common mistake here is to take the derivative of both sides. Make sure you don't do that. You had two stopping conditions, and that was a 0 in the u column or an integratable product in the UDV problem. And that third one is if you see the original integrand in the product. So, and then here is the what happens in each one of those three cases. Case 1, assemble the antiderivative with no further integration. Case 2, assemble the antiderivative and subtract the final product. Integrate, or add or subtract the integral of the final product, and then integrate. And then case 3, assemble the antiderivative and then solve for the unknown integral. So we'll take a look at check your understanding. We'll see which of those three cases we need to use. Oh, I should have written here is the tabular method is kind of an optional method. Okay, maybe I'm not going to write it because I want you to learn this method. It really does speed things along. So Ron's familiar, Scabbers the rat is lost again. Scabbers' location on the Marauder's map is given by this equation where x and y are coordinates on the map. So what is Scabbers' y coordinate when x is equal to 4? So let's do this. Let's integrate this from 0 to 4. Actually, let's find our antiderivative first. So what is the antiderivative of t plus 1 and e to the negative t, and that should be a dt. Okay, let's separate this into factors. You've got t plus 1 as your first factor. You've got e to the negative t as your second factor. Algebraic, exponential. That means that your choice for u should always be that algebraic over the exponential. And dv is going to be e to the negative t. Let's take the derivative of u. The derivative of u is 1. The integral of dv is negative e to the negative t. And if I look across and I multiply this, this is a integratable product. So I could have stopped here, but I also see that this is a 0 and my eyes are getting big. If I take the derivative of 1, I get a 0. Antiderivative is positive e to the negative t. And of course, that 0 means that I don't have to do any more integration. So I'll just assemble it from here. My first product, that's a positive t plus 1 e to the negative t. Sorry, negative e to the negative t. My second product is negative, so minus 1 e to the negative t. And that is the antiderivative. Let's make that look a little nicer. Factor out an e to the negative t. I think I should factor out a negative e to the negative t. And out of this first one, I know that this is a little bit algebraically tense, I think. If I factor out a negative e to the negative t, I'm left with a t plus 1 from that first term. And in the second term, if I factor out a negative e to the negative t, I'm left with a positive 1. And then, of course, plus constant. That gives me negative 1 over e to the t multiplied by t plus 2. Okay, so that is pretty nice. Let's do our definite integral now, which is 0 to, let's see, his y coordinate when t equals 4 is equal to the integral from 0 to 4 of t plus 1 e to the negative t dt, which is equal to negative 1 over e to the t plus 2, evaluated at 4 and 0. Now, don't take for granted that your second addend here is going to be 0. Make sure you do that substitution. So, negative 1 over e to the 4th multiplied by 6. I think I'm just going to put the 6 up here. And then minus, and if I put a 0 here, I get 2 over e to the 0. Simplify that. That is, what is that? 2 minus 6 over e to the 4th power. This lands us at 1.8901. So Scabbers is at 4, 1.8901. So that's our look at integral by parts, integral by parts tabular method. So hopefully that's useful to you. I do recommend you get pretty good at this because it works for every integral by parts, and it does make things go by a lot faster. So just be careful of those things that I warned you about, and you're going to be great. So see you next time. Have a good day.